The force exerted between two charged objects, known as the electromagnetic force, is one of the four basic forces found in the universe. In this experiment, the relationship between force, distance, and quantity of charge will be examined. Two conductive spheres will act as charged objects. One sphere is fixed to an insulated stand which moves along a linear track. A scale mounted along the track allows the distance between the spheres to be measured. The second sphere is mounted on the arm of a delicate force measuring device known as a torsion balance. The torsion balance consists of a fine wire strung between a fixed post and a rotating dial. Attached to the midpoint of the wire is a horizontal arm from which the sphere is suspended. A force acting on the sphere will cause the arm to deflect from its rest position. As the dial is rotated in the direction opposite of the deflection, it places a twist in the wire, exerting a torsional force opposing the electromagnetic force on the sphere. Continued twisting will return the deflected sphere to its original position, at which point the torsional and electromagnetic forces will be exactly equal and opposite. The angle of twist indicated on the rotating dial is directly proportional to the force, according to Hooke's law, and will be used as a relative measure of the torsional force's magnitude. A 5,000-volt DC power supply will be used to charge the conductive spheres. To investigate the relationship between distance and force, the torsion balance is carefully zeroed, and the suspended sphere is charged. The sliding sphere is charged and is moved to a distance 5 centimeters from the sphere attached to the torsion balance. As the sliding sphere is brought near, the electromagnetic forces of repulsion cause the suspended sphere to deflect away. The dial is then rotated until the sphere returns to its original location and the forces are balanced. A relative force measurement of 175 and a distance of 5 centimeters is recorded. The spheres are separated and recharged by the power supply. The sliding sphere is then positioned at a distance 7 centimeters from the suspended sphere. At this distance, a torsional force of 111 is needed to balance the electromagnetic force. This procedure is repeated for distances of 10, 15, and 20 centimeters. At 10 centimeters, a torsional force of 55 is measured. A force of 24 is needed to counteract the force of repulsion when the spheres are 15 centimeters apart, and at 20 centimeters, a torsional force of 13 is recorded. Plotting force versus distance yields a hyperbolic curve, indicative of an inverse square relationship. A plot of force versus 1 over the distance squared verifies this relationship at the larger distances, but indicates a deviation for small values of r. This deviation is caused by error introduced in measurement. At small distances, the repulsive forces cause the charge to migrate on the sphere to a point of minimum electrostatic energy. With charge unevenly distributed, the spheres no longer act as point charges, and the force measurements are artificially lowered. Applying a correction factor to the 5 and 7 centimeter data points results in a true linear relationship between force and 1 over the distance squared. To study the effect of charge on electromagnetic force, the distance between the spheres will be held constant and the quantity of charge will be varied. The two spheres are fully charged and the sliding sphere is moved to the 7 centimeters mark. The dial is rotated until the torsional and electromagnetic forces are precisely balanced. A force reading of 110 is recorded. The quantity of charge on the stationary sphere is halved through contact with an uncharged sphere. The torsional force is now greater than the electromagnetic force, causing the balance to be flat. The forces are rebalanced, and the torsional force of 50 is recorded. Contact with a second uncharged sphere halves the charge on the fixed sphere once again, and a reading of 22 is taken for the torsional force. Plotting force versus relative quantity of charge yields a straight line, indicating that force is directly proportional to quantity of charge. It has been determined that electromagnetic force is directly proportional to the quantity of charge, and is proportional to 1 over the square of the distance between charges. Charles de Coulomb made this same discovery in the year 1788 using a torsion balance apparatus. Coulomb found that electromagnetic force is equal to a proportionality constant, K, multiplied by the quantity of charge on the first object, times the quantity of charge on the second object, divided by the square of the distance between them, an equation that is now known as Coulomb's law.